All right, our last talk of this session is we're going to hear from Daelcheol Kim, who's going to tell us about phase transitions and the speed of spread.
Um, Thank you for the opportunity to speak at this nice workshop. Um, okay, let me just check. Okay. Oh, today I'm gonna talk about. Oh, first, my name is Daelcheol Kim. I'm from Department of Mathematics at UIUC, and this work is jointly with Shend Chatterjee and Partha Dey. Partha Dey is my advisor. So the talk will go like this. First, I introduce what's the first passive percolation briefly, and there are two motivations, which is long range one, and the other one is heterogeneous. And the fifth one is our main model, inhomogeneous long range passive percolation. And then I'll show you some simulations for this model, and then close this talk with the connection to evolutionary games. So what's the first passive percolation? So imagine you have some spatial network, and every edge has some like non-negative random noise or random edge weights. And then you can think about like 2 points U and V, and there's so many routes. Then each route we can define passage time, which is defined as a sum of all the edge weights along the paths. And then we are interested in the first passage time, which is defined as infimum over all possible paths here. So it's the minimal possible time to get from U to V. And the minimizer, we call it geodesic. So the first passage percolation is the mathematical studies of the fastest route in random network. So everything clear here? Okay. But in the real world, it's not, the spread is not that like way that it's local. I mean, it doesn't need to be spread by nearest the neighbor path, something like this lattice structure. So the first motivation is it's very non-local. Like for example, an ember can fly miles away in the wind, or uninfected people might get on a plane. Infection might spread from here. It's very, very long range, right? So the Mollison, he considered this model and analyzed it at 1972. And we formalize it as mathematically as a long-range first pass percolation like this. So the base graph is just lattice, d-dimensional lattice CD, but now every pair is connected, and every pair edge, they have some I at the edge noise. But the total weight becomes, you have to pay the distance to the alpha times some random noise. So if alpha is high, then you have to pay a lot to get a long jump. And Chatterjee and they in 2016, they considered the case when the random noise is exponentially distributed. So here I'll introduce some main results for this model. So this is the main result for this. And here Tn is the first passage time of when you travel distance n. And the y-axis, the parameter is alpha, which is the distance penalty. So if alpha is less than d, it percolates immediately. When you start percolating, then it's just reach everywhere. If alpha is between d and 2d, that takes a polynomial of low times, but which is still faster. That means it spreads exponentially fast. Alpha is 2d and 2d plus 1. That exponent alpha minus 2d is less than 1, so it's faster than linear. So we call it superlinear regime. And alpha is greater than 2d plus 1. We cannot use the long jump anymore because long jump is highly penalized to use it. So it becomes linear. Okay, so the second motivation is in the real world, not every individual or every location are identical. So it's more like heterogeneous. So Dear Donut and other people, they pointed out that there's some source and their target. And if the source activities is high, or um, imagine you have like many followers in Instagram, then information can spread very fast. And also target susceptibility, and you have more attractive, then also the information can be spread so fast, or epidemic can be spread so fast. So that's quantified as AX and BY. Then the transmission rate, here rate means the speed of this spread. That is proportional to AX times the BY and some spatial kernel. Spatial kernels comes from the long range structure. Okay, so to capture this, we introduced our main model, which is the inhomogeneous LRFPP. So without denominator, it's exactly the same as the long-range first-pass percolation. But here we divide by Vx, Vy, which is the random weight on each node. So that represents the source activity or susceptibility or your like followers, something like that. So if V is high, the passage time becomes decreased. Here, so the vertex weight, we assume V is greater than V is, it's roughly behaves like V to the minus gamma as gamma goes to infinity. Because we are interested in the larger V, we only assume this. For the edge noise, we are interested in small noise, so we only assume this lower tail of edges like this. If it is too mathematical, you can just think about this. Alpha is just distance penalty. Small gamma means it is likely to have like large vertices. We call it hub. Small theta means it's likely to have some small noise. So this is our condition. And the main results is as follows. Basically, the previous diagram has only on the right side of the diagram. And we have 4 more regions on the left, which I call it hub-dominated regions. And on the right, I colored the cool tones colors. So I call this as edge-dominated regions. So here Tn is the same as the first passage time of the travel distance n. You can see that the x-axis is the gamma, which is the tail exponent of the vertex weights, and alpha. Y-axis is the same as alpha. And also you can observe that if alpha is increasing like this, and the passage time increasing to 0 to n. So the one more thing we can observe is there's a gamma is equal to theta, and this line is exactly the boundary that we divide as a two mechanisms, like hub dominated, edge dominated, which I explain it shortly. Okay, so this model is not only extend the edge weight as the t to the theta, because if theta is equal to 1, then it becomes the exponential 1 case. But also it extends as the vertex weights, which represents the heterogeneity. Okay, so hub mechanism is the optimal path. They try to optimize their passage time by using exceptionally large Vx here. So when there's a source and target, they try to use very large vertex weights here and pass through it and go to the target. That's the hub dominated, like hub mechanism. I just call it hub mechanism. And if there's no larger hubs, then they try to minimize the random noise here. So they're finding very unusually cheap edges. So that's what we call is edge mechanism. For the vertex, it has some fancy name hub, but I was not able to find some fancy name for this mechanism. So I just call it edge mechanism. Okay, so let's compare the previous classical LRFPP, which is homogeneous case, and this is the inhomogeneous case. So we have 4 more regions here. And as I mentioned, if theta is equal to 1, then it exactly matches as on the right of this diagram, and this diagram is that exactly matches. So it not only generalizes the random edge noise and also the vertex weights. And there's also one more region, which is order 1. That's the new region. And the new phenomenon is they compete like hop shortcuts and rare edge shortcuts by this gamma is, like roughly speaking, gamma is equal to theta line. Okay. Let's see some simulations for this. This is the simulation for tight region, and this is this. I mean, the left picture is always hop dominated, right picture is always edge dominated. So left simulation is the tight region. You can see that it's very sparse, or like there's no like central some big clusters here. It looks like very like starry nights because there's so many hops, it jumps like everywhere. So it looks like this. On the other hand, the right picture is there are no many larger hops, so they try to minimize the edge weights. So it looks like some bigger clusters and small clusters and some hierarchical structures like this. Move on to the sublinear, or we call it superlinear because it's faster than linear. It still has some bigger jumps, but it's not that big as before. And look at the left picture, which is hop dominated region. Because it's hop mechanism, so they are trying to jump more. So their boundary is very rough and more jagged compared to the right, and it's more smooth. And that's the observation of this picture. And move on to the linear. So it's more, so in this case, it's more uniform and isotropic, and also boundaries are more smoother than the hop mechanism case. And they have only one cluster, but there are some small islands, but basically one cluster. So, okay, any questions? Okay, yeah, let me just briefly explain how to prove this by showing some pictures. It's not mathematical. So the first passage time is defined as infimum over all paths. So proving upper bound, we just construct near optimal path. We don't know how the exact optimal path, but we can still construct the near optimal path. So this is the strategy. You don't need to read it. Just see the picture. So first, I want to start from 0, which is source, and this is our target, and draw some big balls of scale n, which is the like middle point of this 0 and nx. And then choose the biggest vertex at that ball. That's the x0. And then next row, use smaller scale of balls. And then choose some top vertices. Here, I chose 4 vertices each. And then think about all the edges there. And here, I need to choose the minimizing the edge and then connect it. And then do the same process. Choose some large vertices and then minimize edge and then connect it, and so on. So if it's very close to here, then at the last step, it's just directly connected. That's how we construct the upper bound path. And the connections to evolutionary games is so this model is actually does not give the like game rules, something like that, but it's so anyway, so EGT requires some contact or dispersal, any like base geometry, but So this model, like rather than describing some payoff dynamics, it provides some random arrival time geometry, so random game board, something like that. So it can explain how fast the strategy or mutant to reach other person. So by explaining both non-locality or heterogeneity, so our model can capture more realistic spatial setting. So the main message here is the geometry of spatial spreads changes qualitatively when offset and ratio search competes. Yeah. That's for my talk. Oh, yeah.
Can you speak or
Is it?
my understanding is that you derived up the bound path. So my question is, I mean, how much you are confident that this upper bound, I mean, derived by the approximate path, capture the correct order? Or do you think that if you find a better path, somehow this, I mean, order estimate you found, right, might improve or?
So passage time is defined by some
Right.
infimum, right? So as I mentioned, upper bound is just any path you can think about is upper bound.
Yeah.
But the lower bound is much harder because you have to consider all paths infimum, right? So in that case, we use some very technical mathematical tool, which I didn't explain it here because of time. So
you have that result as well.
Yeah.
Bound result as
yeah,
well.
upper bound and lower bound. Yeah, matching upper and lower.
Okay.